On the top of page 2, we are learning about percent error. And percent error is, first of all, going to be a percentage. And what we are measuring with percent error is how inaccurate something is. So it's a measure of how inaccurate something is. So to measure the inaccuracy, that's not a good thing. So that means that if you are highly accurate, if you are getting the correct answer, if you do something perfectly, then you would have a low percent error. So high accuracy equals low percent error. As with any percentages, you are always going to, first of all, make sure that you express your percent in the unit of percent. So you're going to draw a percent sign. That will get you at least a point on this. So if I ask you to calculate percent error, and you don't remember the formula, and you don't remember how to do it, and you don't know what to plug in, and you don't understand anything, but all you understand is that, hey, I need to put this in a percent form, and you show me that, I'll at least give you a point. So partial credit is huge in any kind of math that we do. Any percent is going to be calculated by taking the part that we are interested in over the whole value, and then you need to move the decimal 2 places, or you can do that by multiplying by 100. So that is for any percent ever. So for example, if I asked, what is the percentage of students in this room who are wearing tennis shoes today? You would count how many students who are wearing tennis shoes, divide it by the total number of students who are in the class, and that would give us the percentage that we're looking for. The percent error formula is calculated by taking the true or the real or accepted or actual value of something and then subtracting from that the measured value and then dividing by the actual value. In this formula, we are going to use the absolute value. So I'm drawing like absolute value lines. That means that it is always positive. Because what we're really concerned with is what is the difference between the real value and the measured value. We don't care if it's a positive difference. We don't care if it's a negative value. We're trying to see how far away from the actual thing you are. So in the example that I gave a minute ago, if I say that I'm 5'6", and that is my measured or predicted or whatever value, but my actual value is that I'm 5'5", and I do 5'5" minus 5'6", it's going to give me a negative value, but we don't care. All we care about is that I was an inch off. It would be the same percent error if I measured the other way as well. If I said I was 5'4", and I'm actually 5'5", it would give me the same percent error because it's how far away you are from the real thing. And then again, if you need the reminder to multiply by 100 so that you move your decimal place twice to turn it into a percent, that's good. And then when you express your answer, it's going to equal something percent. So you're going to put a percent sign at the end always. So example A here says Jenny massed a 116.3 gram object. Her first measurement was 175.6 grams, and her second measurement was 175.3 grams. Calculate her percent error for both measurements. So as you read through this, it's going to be a really important skill to be able to pick out the necessary values and then associate them with whatever it would be in the context of our formula. So if I'm looking at this and you read Jenny massed a 116.3 gram object and you don't know what to do with that number, skip it and keep reading and see if it makes more sense at the end. So if I see this, her first measurement was 175.6. Does that sound like it's an actual value or a measured value? What is it? Measured. And specifically, it's going to be the measured value that we use for this calculation right here. So this is going to be measured number 1. So that's going to be the value that we plug in right here when we do her first measurement percent error. Her second measurement was 175.3. So that value is going to be what? Are we going to use that? Are we going to ignore it?
Value for the second.
Measured value for the second trial. So measured number 2. So I have a measured value for the second trial. I have a measured value for the first trial. In order to calculate percent error, I need an actual value. Do I have an actual value? If so, what is it? There's only one other number in the question.
Not answering that, I'm going to give someone 116.
116.3, perfect. So 116.3 is my actual value. So when we plug this into our formula, we're just following exactly what it says right here. So I'm going to plug in my actual value of 116.3. I'm going to subtract from that my measured value for trial number 1 is 175.6. And then I'm going to divide that by my actual value. So I'm using the same number twice in this equation, so 116.3. Don't forget to make this the absolute value. So when you look at these numbers, just glancing at it, you should know that when you subtract 116.3 minus 175.6, it's going to give you a negative number, but we don't care that it's negative because we're taking the absolute value. It's going to always be positive. So absolute value lines on either side of that. And then the other part that I don't want you to get confused on, also multiply by 100 at the end. I usually forget to write that, but the other part that I don't want you to get confused on is order of operations in your calculator. Your calculator knows order of operations. Do you remember the PEMDAS thing? Parentheses, exponents, multiply, divide, add, and subtract. Have you learned that? Okay. So your calculator will always do order of operations in the correct way, but it's up to you to give it good input. Meaning, if I plug this entire thing into my calculator, the calculator is going to prioritize division before subtraction, and that's not what we want. We need to do 116.3 minus 175.6, and then I hit enter so that I get an actual value there, and I force it to do that operation first, and then I'll divide by 116.3. And then to move my decimal place over twice, I can either just do that in my head or multiply by 100. And again, we ignore the negative since we're taking the absolute value, and this is going to be rounded to 2 decimal places. So 50.988 would round up to 50.99. So this would be 50.99%. So using the values that we already identified for her second measurement, I want you to use this same equation and calculate on your own what her percent error would be for measurement number 2. I'll pause, and then we'll go over the answer in a second. Her second measurement percent error, is going to be calculated pretty similarly to the first one because it's the same object, so our actual value is the same. We use that same number, so I'm going to use 116.3. We subtract her second measurement value of 175.3. And then I divide that by the same actual value of 116.3. I still take the absolute value, so don't forget that it's going to be a positive number, even though what you actually get in the calculator is negative. And then when you plug this in, you should have gotten 50.73%. The other thing that I want you to know is how you're going to be graded on these questions. Whenever we do math in this class, I give you as much partial credit as I can possibly give you. So you will always get a point for the correct number in the correct place in the equation. You'll get another point for the correct number in the correct place in the equation. You'll get another point for this correct number in the correct place in the equation. You'll usually get 2 points for your correct calculated answer rounded appropriately. And then you'll get a whole nother point for just showing me that you understand the unit that we're using. So in this case, that's a percentage. So that means that this kind of question would be worth 1, 2, 3, 4, 5, 6 points. And same thing over here. It would be 1, 2, 3, 4, 5, 6 points. The other part of this partial credit thing is that if you only typed this into your calculator and you didn't show me any work, and all you did was tell me 50.99, you didn't include a percent, that is 2 out of 6 points, and that is not enough to pass. So the expectation is that every single time we're doing math, you are showing your work, and I will always show you exactly how it's graded. So for percent error questions, this is how I want you to show your work. I want you to show me what number is identified where. You don't have to show the times 100 because I know a lot of you can do that in your head. And then the other piece of this is that if you don't remember how to do it, if you panic on your test, if you freak out and don't understand which value is which, but you understand, hey, I'm calculating a percent, and all you do when you see this is you just write a percentage sign, I'm at least going to give you 1 point. It's at least showing me that you understand what you're eventually looking for. So as the year progresses, our formulas get a little bit more complicated, our calculations get a lot lengthier, and you're able to show me pieces of understanding here and there, so you're rewarded for that in that way. Make sense? Awesome. Let's go ahead and finish up with this last example. I want you to try it on your own. Oh, let's do A and B first, and then we'll try this one on your own. Sorry. A and B, it says which measurement was more accurate? So more accurate translates to a lower percent error. So a lower percent error would be which trial? 1 or 2? 2 was technically lower, so that would be 2. And then were her measurements accurate, precise, both, or neither? Yes, I would agree. So 175.6 and 175.3 are pretty close together. I would definitely say precise. The real answer, the right thing, the true value was 116.3. And 175.6 is pretty far off from that. 50% error is a pretty big percent error. So I would not say accurate. That means it would also not be both, and it would not be neither. So I would say precise. So keeping in mind what each of those mean, I want you to try example C on your own. So reading the student's data and the real density that you're using. So the actual value that you're using is 1.59 grams per centimeter cubed. So keep that in mind. Work on parts A, B, and C for example C there.